So, welcome back friends. Today we are continuing our discussion on quantum field theory and quantum entanglement. In the last class we have been looking at a development of the quantum field, the quantization of the quantum field, and we have built this entire set of states which are essentially harmonic oscillator states for a given momentum mode essentially, and this we have written in this particular fashion, which is A dagger A acting on the vacuum essentially. And this Hilbert space, this large Hilbert space we started talking about is nothing but you have is nothing but something called the Fock space. This is what we introduced last time essentially. And then I also gave the interpretation in terms of the particle, because each particle, each state essentially, once if we act acting on with a dagger, it creates a state of a particular energy, and that state also has a definite momenta essentially. So, for each state it has a definite momenta and a definite energy, and so we can interpret it as a particle essentially. So, every excited state has a definite mass, definite energy, and is a particle in its own right. And so, you have multiple excitations, you have multiple states, and the Hilbert space corresponding to this multi-particle system is called the Fock space. This is where we stopped last time essentially. Yeah, we will look into more details today essentially. So, continued. So, we will so we have taken a single scalar field, real scalar field, and then quantized it, and this gives you this multi-particle Fock state and everything essentially. So, we have seen the procedure how to do it. Okay, now there are some subtleties. There are some subtleties associated with this thing. For the first one is associated with the vacuum. So, let us look at the vacuum energy. The vacuum energy is okay. So, the Hamiltonian, let us remind ourselves what is a Hamiltonian. Is essentially this integral of d cube p 2 pi by cube omega k ak dagger. This we have seen this expression several times, ak dagger ak. Okay. Now, you can use the commutation relations, and then this becomes d cube p 2 pi by cube omega k ak dagger ak plus 1 by 2 pi cube delta cube of 0. This is you can see that this just becomes delta cube of 0. So, it is and you are sitting at an infinity, because this delta cube is delta of 0 is essentially this the 0 point energy essentially. Okay. Now, this integral is one of the first infinities which we encounter. Okay. So, this is one of the first infinities we encounter in field theory. So, how is this an infinity? Because what we see is that, so if we put it here, this has an infinite, there are a couple of Infinity is one coming from the large volume of the space, which is called the infrared infinity. Of course, you can always remove it by taking a finite amount of space, and you can re-express everything in terms of energy density. But then there is the other one, which is just omega k for large k values. Essentially, when the limit, when large k or the p, which for a very large p, the integral again vanishes essentially. So, you have a large integral which is which just vanishes essentially. So, some notational problem. So, this I think we have been using k here, okay. So, this fixes the notational problem. So, this for a large k you will have another infinity, and which is called the ultraviolet divergence essentially. So, in some sense you can think in terms of both, there are both infrared and ultraviolet divergences, but the bigger issue is the ultraviolet divergence, which is really large, huge essentially. So, so let us understand the vacuum. So, the vacuum is defined by a k acting on k is equal to 0 for all k, okay. So, the energy of the ground state H of 0 is equal to E 0 of 0. This is equal to integral d cube k 1 by 2 omega k delta cube of 0, all acting on 0, and this, as we have seen, is just an infinity of 0, infinity. Okay. So, this is nothing but the 0 point energy of large number of harmonic oscillators sitting here essentially. So, because of the large number of harmonic oscillators. So, this is just coming from this equation here, we just put it back acting on it on a state essentially. And now, what we can try to resolve is we can say 2 pi cube delta of 0 is equal to limit L tends to infinity. Okay, you can express this delta function in terms of some large volume L by 2 plus L by 2, okay, d cube of x e power I kx, okay, in the limit k tends to 0 essentially, in the limit k tends to 0. So, this is a delta of k, the e power, this is just an expression of the delta function in terms of a summation over all the plane waves essentially. So, this we can this expression, I guess all of you know this thing essentially. So, this is equivalent to limit L tends to infinity minus L by 2 d cube of x is equal to b. Okay. So, this is, we set a volume to be this particular fashion essentially. So, we just write it in this particular fashion that there is a volume, but then there is still, you can take in this volume, define, okay, we can make a definition of this type essentially, that you have a box or a okay, it's a where V is the volume of the box essentially. So, you can express it in terms of the box. Here L is the length of the box. So, what I did is sort of box normalization. So, you put it in this particular fashion, express the delta function, and so this you think that would resolve the issue. But what happens is, if you have, you can define epsilon 0 is equal to E 0 by V, okay, which is the volume, which is equal to again d cube of p or d cube of k 2 pi cube 1 by 2 omega k, which is an infinity for large volumes essentially. So, you put it back here. So, the point is that you could resolve the delta function here. You could resolve, thinking that you could resolve the delta function sitting here by introducing a volume, but then you can take the volume out essentially, and then you still have this integral over large k essentially, over large large momenta, okay, which is again an infinity. This is called an ultraviolet divergence. Because this occurs at k tends to infinity essentially. Okay. So, this infinity, the other infinity which we see appears at k tends to 0 is sometimes also called infrared divergence. So, what we have already seen is that the vacuum is besieged with the infinities. You can get rid of the one of the infinities by doing a box normalization, but the other infinity still exists, which is the ultraviolet divergence, which goes for large k values essentially. So, this integral means that you need a cutoff, okay, you need a cutoff essentially, and so the way of doing the cutoff is something okay, is just by subtracting the cutoff essentially. You say that this we also encountered earlier essentially, remove the infinity of the vacuum by sort of subtracting it. So, the basic idea here is that the physics energy levels and everything only depend upon the differences in the energy values. Since the vacuum is always constant for all energy values, this can be completely removed essentially. You can remove the entire thing essentially and work with only the energy differences or the state differences. So, one can remove the infinity, one can remove the constant, this is some sort of a constant essentially, a constant for all states essentially. So, this is a constant ground state, constant ground state, and define a new ground state such that its energy is 0. So, you just say that you have a ground state now but which starts at 0, but it does not start at large infinity essentially. So, you can remove this infinity because what matters for me is only the differences in the energy states essentially. Okay. This process is called normal ordering. Okay. Okay. So, the basic idea for the normal ordering is that the prescription is that you typically say H, if you define H is equal to, with two dots here, this is the definition of the normal ordering notation for normal ordering. So, this just becomes integral d cube p or k, because our notation we are using k or p, whatever, meaning it does not matter, k 2 pi cube omega k a dagger k a. So, we removed the other term essentially in the definition of the Hamiltonian, we removed the term which is a dagger. So, we removed this term. The basic idea is that here we only keep the terms, or we all the terms, all the annihilation operators, all or expressing normal order term a dagger expressed becomes a dagger a. That is the basic idea essentially. All the terms have the annihilation operator towards the right. Okay. So, with this definition, so if this definition of the normal order Hamiltonian, H acting on 0 will just give me 0. So, the basic idea is that all the annihilation operators should always be on the right essentially. So, if you have a states bunch of states essentially, okay, if you have a bunch of fields, okay, phi of x1, phi of x2, so on, so phi of xn, we will see this in more in interaction picture. So, you basically make sure all annihilating operators are always to the right. That way we defined what is the normal ordered the new Hamiltonian or the new normal ordered Hamiltonian, and in fact we will always deal with normal ordered operators in field theory. But does it mean that because you have ordered normal ordered the operators, does it mean that the vacuum does not have any fluctuations? Yes, the vacuum will still have fluctuations, but as the vacuum will still have fluctuations, and these effects are real. These effects are actually real, meaning you can actually, one of the consequences of major consequence of this particular process is the so called the Casimir effect essentially, which we will not go through, we will not I will only mention in passing. Okay. So, this Casimir effect is real, you have the will have fluctuations and the effects are real. So, this is best essentially understood in terms of the Casimir effect when these boundary conditions on the field fluctuations will play a major role essentially. So, this is called the Casimir effect. This will be part of your assignment essentially. So, I will not have time to cover it, but there are wonderful books and everything which cover this beautiful physical picture essentially. So, now that we have defined particles, so so the excitations of the field, so we have defined the vacuum, Now we also have defined the particles. Essentially now it makes sense that you have particles are defined as p or the momentum state is a p here. Okay, you can have a p dagger p acting on vacuum. So this is a well defined momentum state which you can have. As we already discussed, it has a definite momenta, definite energy, and so on. So this can be interpreted in terms of the particle. Now the point is that so we have defined that you can always have multi-particle states. You have vacuum, AK dagger on vacuum, and so on. So you can have AK, AP, AR acting on the vacuum, and so you have multi-particle states, and this will lead up to your Fock state. Now the point is that you should always remember the particle number is essentially you have this the number operator essentially. Okay, now the point is that there is one important point I want to make essentially that when we say these particles which I introduced in the last class, and so these are not localized particles essentially. So these are not localized in a specific space in any way. So what we have essentially is some momentum state. Okay, they are all momentum eigenstates essentially. So these are not particles and their subtleties. So they are not localized in space, they are momentum eigenstates not localized in space. This is obvious. There is also one more important point that essentially which we learn in quantum mechanics, that momentum eigenstates, they are not normalized. Okay, these are unnormalized wave functions essentially. So these are unnormalized, they are not normalizable essentially. Actually to be so you cannot normalize them. So they don't produce so the operators, the phi or the A dagger, the momentum space operator, the creation operator doesn't really produce you sort of normalizable okay, operators, but so what we say, these are operator valued distributions. This is a very important thing which we have to understand. These are operator value distributions. These are the states which we have essentially, the phi which we constructed essentially. Okay, are so these are not really functions. Functions, the phi fields, essentially the scalar field, the scalar field. So the scalar field acting on a vacuum gives you a particle, but that particle is not really normalizable, so it doesn't give you a good field essentially. But then you can create wave functions essentially. So you can create okay, let me okay can create wave functions, wave functions. So something like with smearing function. Okay, so you just smear it a little bit, and then so you can have a state phi integral d cube of k pi cube e power minus I kx, some function of k, essentially you can take some function of k, okay, and then k, okay. So this is one of the very subtle points essentially associated with the fields. These are not really, when we started the thing, we say that I take a scalar function and then I quantize it and everything. But in reality, these fields, when you quantize them, actually they turn out to be some sort of operators which are they give you operator value distributions. What we mean by operator value distributions is that they, even though their vacuum expectation value is meaning finite essentially. So if you take phi of x is equal to 0, so the vacuum expectations value is the vacuum expectation is sort of well defined, okay. But then if you take a fluctuation around the vacuum expectation value, okay, this is infinite fluctuation okay. But then we can always like I said essentially construct wave functions. We can always construct wave functions as here, and then now you can choose, okay, this is what we mean that these are distributions which are operator value distributions, okay. The fluctuation is infinite, but its vacuum expectation value is correct. But then you can always construct well defined wave functions, and these wave functions you can take, say for example, phi of k to be a Gaussian. Take for example k to be Gaussian, and these are partially localized and in momentum and space essentially. So you can always construct wave functions, but the important subtle point is that the field operator creates unnormalized eigenstates essentially. These are unnormalized eigenstates and not normalized momentum states essentially. And taking them, you have to smear them with some Gaussian or something to create well defined wave functions, okay. This is a very important point. So in this class what we have learned is a couple of very important points. One is about the vacuum. There are infinities galore in the vacuum essentially, and the way to deal with them is by doing something called so normal ordering. So by doing something called the normal ordering, okay. So we do the normal ordering, we take all the A dagger operators on the right and move them to the left, so that only the A operators, the annihilation operators, are always in the right essentially for every operator. And the notation is that we keep an operator and put double dots on both sides essentially, colon on both sides, and you take this thing and you make sure that all the A operators are also always on the right essentially. So with this and the second subtlety, we saw that this the states which are obtained by this quantization are momentum eigenstates. They are not normalized essentially. They are in fact these phi's or the the scalar field which we have thought about are not really functions, and these are actually operator value distributions. So, when somebody tells you that it is a distribution, you should not be worried essentially. So, it is true that because they do not produce anything. So, they do not produce normalized wave functions, but you can create well defined wave functions by smearing them with a Gaussian like I have shown here essentially. So, I will stop here and then we will continue in the next class essentially, and then we will move to a slightly more complicated scenario starting with a charge scalar field essentially, with a charge scalar field, and then look at the quantization of the charge scalar field, and we will start looking at how to write the interaction picture. Okay. Thank you very much. I will stop here essentially. Thank you very much.